heading.
Oh yeah. Oh yeah. All right. So we had a bit of a look at commercial foundations and some of the footings. Now I just want to touch on some of the different types of floor systems that you can use. There's quite a list. All right. So beam and slab systems out of concrete. Pre-stressed concrete. Pre-stressed concrete is where under loading there's concern that the slab or beam will deflect and go down. So it's pre-stressed a little higher, so then when it's loaded it comes down to flat. That make sense? So if you want a finished product that is flat, horizontal, I shouldn't say flat, under loading, so its own structure and its use. If there's a concern that the structure is going to deflect under those loads, and we don't want that, pre-stressing will put it up a little first, so under load conditions it will then come down to horizontal. And that can be achieved using concrete and steel combinations. So we'll cover this a little in 4005, but it's not just concrete in this system, it's steel as well. And the idea is the reinforcing that is threaded through, which is very strong in tension, so you can pull on steel a lot harder than you can pull on concrete before it fails, it will get pre-stressed and bent using the steel, and then it will come under loading and the compression will do the work that the concrete is known for. So in combination, steel and concrete is very effective. You guys okay? You just having a bit of trouble? Yep. Cool. Concrete formwork and shoring. So we've talked a little bit about shoring already. Formwork is about making a mould, so we've mentioned moulds a couple of times already. Formwork is the proper name for a mould for concrete that's wet and needs to be held in place until it sets. So you make formwork and then you put the plastic concrete in, plasticized concrete, and then it sets, it goes off, it hardens, and you can take the formwork away. Now you can have situations where you can't remove the formwork. It's called lost formwork. So that just stays there forever. So you might make that out of a material that you can afford to look at, or it's too difficult to remove, or it just gets staying in place. So lost formwork, or it can be removable. It can have a texture on it that puts a finish on the concrete so it looks interesting when you take it away, or you might just be able to see the outline. Formwork is typically made of timber, particularly in residential construction. In commercial construction it might be steel, or it might be huge panels of steel with thickness to it, because the concrete slab is heavier typically than residential. Commercial is typically thicker than residential. You need a stronger formwork to hold it. So this might be sufficient, and it's not a very good shape. It's usually a nice shiny, actually I have a better, it's usually a nice shiny black marine grade formwork that's water resistant.
Because concrete is wet?
Yeah, in here. But for commercial projects, you'll often use steel panels that have a structural thickness to them as well. There it is. Form ply. So it's quite heavy duty timber. It's got a lot of strength horizontally into it, but you have to brace that with further support. So this does the work and holds the concrete inside, and it's waterproof. And it's nice and smooth and shiny, so it leaves a nice smooth shiny finish on the concrete.
So you'll also get the steel. So steel can be, it's usually in some sort of a profile, and so you lay the steel across between your load-bearing walls, or your usually load-bearing walls for this scenario, and then you pour the concrete into those steel molds, and that that steel is just formwork. It's not giving the strength to the floor, but the underside of the floor will be steel when you look up, but it's actually a concrete floor. The steel has just been used as a formwork to hold the concrete in place until it hardens. Target in Palmerston, next time you go in there to do your shopping, and when you drive underneath, look up, it's steel. Concrete floor, but it's steel.
You're right.
Yeah.
And you can actually feel that deflecting occasionally. Concerns me. Another conversation. And you'll use temporary props to hold it in place while you wait for the structure to be self-supporting.
Of course. 28 days.
Well done. Precast concrete floor system. So we've talked a bit about precast. Pre is in before, and cast as in mould and poured and ready to go. So off-site and then shipped in. Precast concrete connections, structural steel framing. So we've already talked a little bit about steel and some of the different shapes and sizes that you can get. You build the floor system out of a crisscross of steel members. You can't have all the members going one way, they'll just fall between each other. It has to be crisscross. Steel beams, steel beam connections, open web steel joists, and open web joist framing. I'm not quite sure what open web means, we'll have a bit of a look. Metal decking, light gauge steel joists, light gauge joist framing. So the I-shaped steel beams that we've been talking about, that parallel flange channel, and perhaps even something like the SHS or RHS that I've mentioned, that steel, they're heavy gauge steel. They're quite thick. They're definitely more than 1 millimetre thick. They do very good structural work. They're quite substantial structural, RHS and SHS. They're quite heavy gauge steel, and you would specify them to be several millimetres thick. Whereas this is light gauge steel. Light gauge framing is less than 1 millimetre thick typically, and it's often strengthened by using the shape. So it's actually the shape that gives it a lot of its rigidity. So I can't bend that, not because it's thick steel, but because of the shape. And I can't twist it very easily either. So that's light gauge steel. So there's a couple of different types.
Shape, like actually, originally what they would have done was cut out a whole rectangle. But you know, science and computer modelling has told us that this is as strong as it's going to be, even if we lost this cutout of it. It doesn't need this one because this is the shape that's giving it the strength. It doesn't need this side of the rectangle. So they've decided to not use steel for that side and still retain the strength of that in a profile, in a C section or a Z section that we can see there.
And then it goes on to wood joists and wood joist framing. So on the diagram the other day we were talking about floor framing, and we had the bearers first and then the joists going the other way, and they were giving the floor finish somewhere to sit that wasn't too far apart. So joists are an important phrase that you want to keep an eye on, floor joists. Subflooring, prefabricated joists and trusses, wood beam supports, wood post beam connections, wood plank and beam framing, and wood decking. So there's quite a bit. I don't think we'll have time to go through all of that, but perhaps what we might look at is the concrete beams and slabs and the pre-stressed concrete. That particularly is what we're interested in for AT2. And then when we come back to it, we'll have a look at the structural steel. So it discusses the concept of a floor system and the deflection that can be experienced under load. There's a little note here which is quite good. I think it's with regards to service systems with regards to floors. So sometimes our floor system needs to also account for some of the services, wiring, plumbing and conduits that go from one place to another, from up to below or from across from side to side. Let me just have a bit of a look here and see what it's telling me. We're having a bit of trouble with the zoom in. Apologies. Not before.
The writing of this book is really difficult to read, isn't it?
It's beautifully written.
Lovely. It's really
I'm going to grab it out of the actual physical textbook that I've got. Yeah, page 106.
Which one?
This one, you think that will work better? You're probably right. Yeah, well done, thank you. That will do nicely, thank you. Oh, look at that. The depth of the floor construction and the cavities within it should be considered if it is necessary to accommodate runs of mechanical or electrical lines within the floor system. For floor systems between habitable spaces, so our apartments are definitely habitable spaces, stacked one above another, additional factors to consider are the blockage of both airborne and structure-borne sound and the fire resistance rating of the assembly. Good point. You can embed plumbing and wiring and conduits in concrete slabs, but you have to consider what that will mean for the structural capability of that slab. So if the majority of the concrete is dispersed by pipes and tubes for wiring or water or plumbing, then you might have to consider the depth of that slab to accommodate that. Your other option is to just penetrate straight through and then move along underneath. But then you have to consider how you're going to hide that if it needs to be hidden. Now, on the ground floor of our AT2, we have an open carport where plumbing could move around and be placed underneath without really bothering anybody. There would need to be enough clearance so that vehicles didn't bump into it and damage it, but aesthetically, we're not really worried about what that looks like. But in people's homes, that's quite a different scenario. So a phenomenon like a bulkhead might be used to create a shape that would cover that piping if it were exposed. Or you could have a deeper ceiling and conceal it completely. That would mean that the floor to slab height will need to be greater to still maintain the expected head height of the occupants inside. So there's quite a bit to consider in the design of a project to make sure that all the ductwork gets somewhere to go. I'm hoping to get us an inspection of the Class 2 project that's currently under construction in Palmerston. In the meantime, if you find yourself in Palmerston, maybe going to McDonald's for lunch, just drive towards Bunnings and then very slowly drive past without crashing and have a bit of a look and see. There's the ductwork for the air conditioning is already in place. There's a lot of pipework and things already in place, but it's just raw precast concrete construction at the moment and nothing's all closed in. So it's the perfect time to go and have a bit of a visit. So I'm hoping the owners will let us through. We probably will have to have our white cards to be able to do that. So keep that in mind for when you're getting them, and then we'll see if we can negotiate access, because they won't let us on without them.
Does everybody here have the white card?
Not quite, yeah.
Okay.
You can see quite a bit just from the road, so park at Bunnings and stand and look. And stay there for a while and stare. Like, they won't mind, and do it on Sunday, there's nobody there. But it takes a while to take it all in. You just have to look. You just have to stand there and look. If you just go, oh, and walk away, there's not much that you can take in that shorter period of time. So follow where pipes go with your eyes, see if you can pick out different facets and see what you can see. But the air conditioning ducting is big steel, silver, galvanised boxes, hollow boxes with brackets around them to hold them in place. They're quite deep, so you'll be able to see those really easily. And then the white piping is the plumbing and things like that. And electrical conduits are typically PVC and they're quite narrow, and the examples are over here. They've got different grey and orange colours. So I don't know if you'll see any of these, but see if you can see any of the conduits coming around that wiring would go inside. Definitely worth a look.
So they're putting ducted air conditioning in the Class 2 building?
Yes,
Oh.
it looks like it.
Oh, cool.
And it's quite a few stories of car parks first, so you have to look up. It's usually about a 600 millimetre drop of height allowed for ducting and conduits and things like that. So that's quite a big rise for the structure above where you would normally put it if you were going to have standard construction, no ducting. But yeah, that does appear to be what's going on.
So with ducting like that, in my experience, so where you've got let's just blockwork walls on a very tall apartment building, and we're going for complete concrete construction. A roof slab.
There's a better marker behind you if you want.
This one?
No, the big ones. Yeah.
Let's say we've just got an apartment building and we've got a couple of stories and it's all going to be concrete construction. Just ignore that, sorry, I just got to put on fund. So you might have, you know, as we said, you might have the ductwork that needs to go through underneath that slab. It could be like, you know, pipe work, electrical. If it's going to be big mechanical duct, as Lisa said, that could be like 600 mil. So that will determine what your height is going to be from the underside of one slab to the next. And of course, you may come along and just put a ceiling in here like this.
A little bit more attractive than this one, but of this concept. So CSR, a local Australian company, make excellent different panels and things for suspended ceilings. So these are just hung by little droppers that hold the frame. See the aluminium runners that go this way? And then the plaster tiles just nest inside them.
So this is all concrete. What you can do, and what engineers often like to do, to make, so that we have to think about the thickness of this slab, right? And obviously everybody wants it to be as thin as possible, but the structural engineer needs it to span whatever that distance may be. But what they do sometimes to strengthen the slab is that they'll drop a beam down like this.
One of these?
Yeah, one of these. And then every so often you have that beam down. So that's giving that, it means for the slab that this slab is now only spanning from here to here and here to here. So this thickness can be reduced because of these beams. And then the idea is that you will run your services in the other direction to the beam. So that takes a lot of coordination on a project, because you've got to make sure that all your service engineers are working with the structural engineers to ensure that no ducts are trying to run in this direction, because if the duct runs in this direction, it needs to come down here. You know, it will run in that plane across, and you know, nobody wants to see a big duct hanging down like that. So we've got to make sure that all of our ductwork is able to service all the area that needs to be able to service in this direction only. So it's a lot of coordination when we start to look at structures and services together in bigger buildings, and a lot of that is determined very early in the project, because obviously, you know, before you even apply for planning permission, which we all know we have to tell them the overall height of the building. Well, the overall height of the building is going to be determined by how thick these slabs are, how deep the beams are, and can we get all the ductwork running in between the beams, and do we need to come down another 600 mil per level, which makes a huge difference to the overall height of the building. So quite early on, these are the kind of things, what is the basic structure going to be, and how do we run services within that is a very big question that comes up very early in the project. Any questions?
Those little beams, yeah, so they are not supported by anything.
They reach to the end,
to
the external walls.
To the far side of the building, and then so
yes.
they'll be running in this span, and this one then, yeah. That's what happens. So they're deep enough because they've got the thickness from the top of the slab right down to the bottom to be able to span the entire length or width of the building, as the case may be. Yeah.
Awesome. Brilliant explanation. It's a pretty good indication here of what that beam looks like. So there's reinforcing heading this way, and then the ligatures hook into it, and then there's reinforcing inside the footing itself as well. So steel and concrete work extremely well in combination, because concrete can take a lot of pressure and steel can take a lot of tension, a lot of pulling. And so when you've got something that's trying to stay in place, if it deflects, that starts to pull, and the steel stops that from happening. And there's lots of heavy weight coming down on it, and it would get crushed, but the compression strength of the concrete can prevent that from happening. So it's a brilliant combination. The tricky part is where water gets in. That's why waterproofing is so, so vital, because as soon as water gets into that concrete and it gets into the steel, it rusts it delaminates, it expands, and it pushes the concrete away, and it's completely failed as a structure. So water is the enemy of that combination. It's really, really good as long as it's protected.
But for these concrete constructions, what is the most common solution for sealing?
Suspended ceiling. Or in an apartment building, we would drop the level of the ceiling in, say, our wet areas in the bathroom. We look at it in the afternoon, when we look at our actual building. We might drop the level in the kitchen and the bathroom to be there, and then have to be as high as the top of the room, in the kitchen and the wet areas, and then we would hide all our services in that. That's known as a bulkhead. When you drop it down. So once you drop that ceiling down, we were hiding all our services in there. Yeah.
So normally in a traditional home, you would have the timber trusses, and then they would all be lined up this way on your house, resting on the external walls, and maybe one internal wall. And then you fix these battens underneath them, and you can screw plasterboard, the ceiling lining, to this batten. You can't fix the ceiling lining directly to the trusses because they're so far apart, and there would be too much opportunity for the material to sag under its own weight. So these go much closer together, 450 millimetres apart, centre line to centre line, whereas trusses can be, 1.2 metres apart at sometimes, so too far. So we put these the other way and be able to fix the ceiling lines to that. It's not so easy in a concrete floor, and the flooring in our Class 2 building won't be precast. It'll probably be poured on site. The walls might be precast, but even for our project, I'm probably not expecting that. We would just build the blockwork walls on top of the slabs as we go, so we would build it incrementally going up. Precast is really good for big projects like the Gateway Shopping Centre and things like that, but that's where the skeleton is the structure and the precast is the skin, whereas in this instance it's probably more cost effective and time effective because of the intricacies of the rooms of the sole occupancy units. It's difficult to achieve that effectively with precast, because precast is much better for big expanses of blank walls with maybe a couple of penetrations at most, whereas when you're doing people's homes, there's lots of movement, and block work like that can respond much quicker. And we're very good at building that here. Yeah. So we would build then the floor in place, connect for the chain of strength, and then build the blockwork on site, and then build the next floor, and build the blockwork, and build the next floor. So
all of our walls are load bearing.
Yeah.
Load bearing block wall floors.
Rather than these very squat, short battens in Class 1 and 10, you could perhaps use something that has a bit more height. So there's quite a few different, this is just an example, there's quite a few different light gauge steel structures that you could use to create that same battening phenomenon underneath this steel slab, so that you can fix the same ceiling lining to it that we talked about. So these can be close together, but they're quite deep, and that would allow for that same phenomenon that Sandra was talking about, where the services would have some room. You don't need, for air conditioning, the ducts are very big. They're quite significant. But for standard conduits for split system air conditioning, they're not quite as large. They're usually just pipes with foam lagging around it to keep the cool air in. And the conduits that we've got are quite narrow, so a depth this size would probably be quite sufficient for our Class 2 building, where you could just use battens. The other option, like Sandra said, is to create bulkheads, and that's simply just a frame made out of this light gauge steel or timber. Not typically timber here, but you could. So you just make a box and fix it to the ceiling, fix it to the slab. And then there's room for the plumbing thicknesses. So when you think about the different pipe shapes for services, it's not just the size of the pipe, but also the direction the pipe needs to go in. So plumbing obviously has to run downwards. You need to have a fall in your services. And so where it starts and where it finishes might be a few millimetres apart. So you need to account for that distance as well. There's a height there over the top to the bottom of the fall, not just the thickness of the pipe. So a bulkhead is a frame, like a box, and then you can clad that and just paint over it. And like Sandra said, because you've got the lower head height facility in bathrooms, you can take up that space without having to change the slab height overall. you can afford to come down. And kitchens allow for that as well. And it's a nice way to articulate the design and have differences so that you haven't, so you don't have this massive expanse of space that echoes like a typical apartment might. Lots of hard surfaces because they're easy to look after and clean. They kind of echo and can be a bit impersonal. So to change those heights and exactly differentiate the different spaces can be a handy design tool that also achieves good principles for construction. That statement, it's just a funny note I found, again, the internet, God bless it. Apparently, a new apprentice carpenter was given the job to create the location of something, and it was supposed to be the frame that a bath would sit in, and he thought it was a bulkhead, and so he fixed it to the ceiling in the bathroom instead of putting it on the floor. I'll see if I can find the photograph later. It's really sweet. They look kind of the same. It's just, you know, stilts and a frame. It's just a box. It's kind of cute. What have we got here? All right. Now let me see if I can find some headings. Now what I want to show you is how it all comes together. So we just very briefly mentioned that the most likely construction technique for our Class 2 building is where we'll have concrete poured and then walls built and then more concrete poured and then more walls built, and you just keep going up and up and up. But we also talked a bit about this chain of strength and the connection phenomenon that you have to make sure of. And that's not just the case in cyclonic conditions. Most construction will want to have a connection of those different parts together to hold them in place so that there's no movement. It just shows a couple of examples of how that might be achieved. And these lines are the reinforcing that can be placed through the construction, and then you can have extra subsequent reinforcing coming up and overlapping. So there'll be horizontal and vertical reinforcing that have overlaps within the wet concrete. See if I can find something that's a bit better than that drawing though. It's just...
Don't forget our walls are core filled, so that when you build blockwork, the block itself is not solid, it's got holes in it. So you can still lay the reinforcing into that blockwork and then pour concrete into that, and then you'll also be pouring your floor slabs as well, so you can connect up all the steel reinforcing between what's in the core of the blockwork and what's going to be cast into the slab, and then when you pour, it holds all of that together to build up those connections and make them very strong.
So we've got here a description of a one-way slab, a uniformly thick, reinforced in one direction and cast integrated with support beams. So all together.
Pretty much what I was looking at.
Exactly what you were looking at. The difference then, and this is a joist, this is a one-way joist slab, which is a little different. So there's some additional support here with some joists as well as the beams. So rigidity there. But then it also should go on to two-way. Here we go, two-way slabs. This is probably most likely what we would suggest for our Class 2 construction, simply because of the heavyweight construction that we're dealing with. So there's a two-way slab. It's uniform with the beams, but reinforcing in two directions. So it'd probably be able to span further. So two rows of reinforcing, one at the top and one at the bottom, where it's connected to the beams and the walls as well. Just see if I can see that connection. And then there's a two-way slab with the waffle phenomenon that we were talking about. Come on now. And a two-way raft slab. Just looking to see if we've got the way... this is quite something else to consider in the back of your mind as well. So we've talked a little bit about the point loads down and how we have to have pad footing to prevent that point load from bearing down any further. It spreads the load out. We also have the same phenomenon in an upwards motion underneath a big slab. So thinking car parks, if you've got a point load onto a small surface area coming down from above, you might have failure in some way, so we call that shear, where the edge of the slab above is sheared off from the point load beneath it. So this spreading just moves the load out even further again. So you can have a step down within the slab itself, or you can have, it's not a plinth, I can never remember the name of that. I want to say casement, but I don't think that's it. There's a word for that shape. I'll have a look and see if I can see it on this page. But every single time I go to tell what this is, I say to myself, I'm going to remember it next year, and I never do. It's so annoying. Let me just see if I can see it. But it's a terrific way to spread the load out if you've got significant point load above. So the drop panel, it's a capital. That's not the word I was looking for, but anyway, it is a capital. So in ancient Greek columns, you saw the wider tops, and they had designs, and they were all for different eras. They had different shapes, and the top is the capital of a column. So this is, in fact, correct. It's not the word that I was thinking of, but it will do for now. So the capital at the top here, just to prevent this, see the increased shear resistance. So shear is the kind of phenomenon that you would see if a big piece of an ice cliff fell away and dropped into the ocean. It's a shear cliff, and that piece breaks away and falls down, and it shears off against the surface. That's where that phenomenon comes from. So if you were to have a column that sits underneath a slab, and there was a failure because there was too much resistance here against the force, and it fell away, that would be shearing. And these columns create increased shear resistance to prevent that. So we would perhaps recommend that for our columns in our Class 2 car park. All right. How are we doing for time? Yeah, we have mentioned pre-stress. I probably don't need to go over it, but there's the look at that. It's like I read the book already. So there's a bit of information about pre-tensioning and pre-stressing the concrete and bending it up so that it comes back into place when you load it. It's a terrific phenomenon, really clever engineering phenomenon. Concrete formwork and shoring. I probably don't need to go over this too much, but it's a very good little picture of exactly what I was talking about. So here's the formwork, which creates the mould, and then the little props that keep it in place while you wait for the concrete to be able to support itself, and then you can take it away. And these are the verticals we talked about. So I don't want to say scaffolding, but it's a propping. Yeah, thank you. They're adjustable props underneath, and they often have big timber plates on the top or big steel plates to do that same load spread that we were just talking about, and then you'll have the formwork above that. And it's often ridged steel because those shapes give it strength as well.
So the load spreading, the next time you're walking on the beach and the sand is a little bit soft, see how wide you can spread your toes and not to make a less indent in the sand with your foot. Does everybody know that experience?
Or when you're walking in the snow and you have tennis rackets on your feet.
Rackets and there's people walking the snow like the big.
We're just making this up now. Yeah.
All that is, it's exactly the same thing. All that is that you want to spread the force. So obviously, if I put a pen on a piece of paper, there's a great force where that little tip is hitting that. But if I have something that's a big circle on that and I put it down, it's spreading the same force over a greater area. So we're just reducing the force. So that's what that's all about, having a pad footing. So the column isn't going straight down into the ground like that. It's got something flat to spread the force onto the ground. Similar at the top where you want it to meet the slab, you might have those thickening edges on the top to prevent piercing, I suppose, to prevent that greater force to spread the load.
So section 4.12 just has some notes on precast concrete units. I've got a couple of past students that have taken their drafting qualification into precast drafting. It's a whole range of work all on its own. Skyline Concrete are recruiting as we speak, I believe. The idea is that you specify where the lifts are, because obviously you have to pick this concrete up. So you have to build hooks into it that you can use to collect it. And then you also have to have channels built into it to allow for conduits and wiring and plumbing and things to go through it. There's all sorts of different shapes and sizes. There's limits to how big you can make it. There's limits to the truck that can carry it. So 12 metres long and 4 metres wide is probably the biggest precast wall you might be able to get. And then you've got to specify how they're all going to be built in place and which one's going to go where and things like that. So there's a whole career in that if you're interested.
And
So,
if you're doing a building with precast concrete, you have to do a schedule of the precast concrete panels, the same as you would a door and a window schedule. You have to draw each panel individually and show the openings in it and the thickness of it, and so that you're telling the engineers and the people who are manufacturing the slabs for you exactly what you want, where each of your openings are. It's very precise to the millimetre when you're designing precast concrete. And of course, then the other big consideration is the fixings. How are you going to fix the precast concrete panels to your building, to your structure? Because remember, when you're building that building, you're going to build a structure first. You're going to build column and beam construction, and then you're going to have a whole frame of a building, and you're going to bring the concrete panels, and they're literally called tilt-up panels because they're put on the ground and they tilt them up, and then they connect them to the structure that's already there.
lots of bolts. So a solid flat slab or a hollow core slab, there's single T's and double T's, and then lots of different shapes and size beams and girders. So you can have all sorts of, it's like Meccano, it's like Lego for grown-ups. And then there's information about how a precast slab might sit. So it often has to notch in. You see that resting there? And this is a huge amount of pressure just here. So the shear force here is very significant. So it has to be managed. All sorts of fun stuff.
There's some great precast systems that I've seen back in Europe for, they're actually called precast beams, but you literally build your frame up for your floor. You can use these in housing as well, I love them. And you slot them in like the floor joists.
Yeah, right.
But they're sort of an L shape of concrete. So when you've got them all slotted in, they're like joists, and then they've got a base of concrete that's quite thin. And then when they're all in place, it becomes kind of formwork, and you pour concrete into that as well, and that becomes your floor. So it's a mix of precast and cast in situ all in one. Yeah, they're quite reasonable priced as well for if you want to put a concrete floor in your home.
All right, we might pause it there. It's just a couple of minutes until lunch. I won't start steel framing until after lunch. That's enough concrete for one morning. Does anybody have any questions? Let's just all take it in. So shoring might stay in place forever, whereas formwork might get removed. It can be the other way around too.
Yeah.
But shoring is mostly about keeping earth in place or preventing collapse, whereas formwork's about making a mould for concrete to be poured into. Yeah.
Perfect. Just
like the words come out of your mouth. Yeah.
One's to do with earth, and the other one's to do with concrete, basically. You've got a really short explanation. Shoring is always to do with earth.
All right, let's get back to construction. Exciting. So structural steel framing. Now, our AT3 is structural steel framing, but it's a special kind of structural steel framing. So I'll go through this briefly, and then I'll skip to that version instead. So structural steel framing, it's about girders and beams and columns used to construct a skeletal frame for structures ranging in size from 1 story to skyscrapers. So this squared off phenomena, how the girders and beams are flat, can be made into multi-story. So just about every tall structure ever seen has some system like this. Because structural steel is difficult to work on site, it's normally cut, shaped and drilled in a fabrication shop according to design specifications. So that word shop is a place, another place in the US, they call it shop. So as a result, drawings that are drawn for this fabrication are called shop drawings. Yeah. So another facet of drafting that you could work into. A bit like the millimetre specific precast concrete that Sandra was talking about, this is extremely precise. The threads of steel to the just extremely precise fabrication where big members have to come together and they have to be millimetre perfect. So shop drawings are very detailed. Is it? Wow.
Fitting drawings, like one job could have like thousands of fitting drawings. And
yes.
Because I was a junior, I had to do all of them.
Oh, goodness. Wow. Wow. Yep. once it's done, it can result in relatively fast, precise construction of a structural frame. Structural steel may be left exposed in unprotected, non-combustible construction, but because steel can lose strength rapidly in a fire, fire-rated assemblies or coatings are required to qualify as fire-resistive construction. In exposed conditions, corrosion resistance is also required. So there's a whole discussion further on with regards to steel assemblies and how that all works. It's a pretty good diagram of how it all comes together, which is nice. So the concept that Sandra was talking about earlier about rigid steel sheet becoming a form for concrete as a floor, it has a really good illustration just here. We probably wouldn't have it quite that thin, but it still gives you a pretty good idea of how it would work. And then there's the beam supporting it and the girder going in the other direction. So here we've got a column, a beam, and then a girder with the floor. So it's a system that works together. Just a little indication of how the connections might work. So there are steel plates with bolts through, welded and bolted. And then it depends the size of the plate, the number of holes, the number of bolts, the size of the bolts, all determined by the load and the strength and the size that the steel is specified by the engineer. Oh, and here's our footing that we looked at in 3D and in plan view earlier, just shown in section, how here's the little plinth that helps shed water. There's the steel plate with the bolts through, and it's connected into the pad footing beneath. Ours might come down a lot longer into a pile that might resist uplift in cyclonic conditions, but the principle is still the same. And there would be 4. You just can't see the other 2 that are on the other side. They're directly behind those in the drawing. So there's one-way beam systems, two-way beam systems, and three-way or triple beam systems. So that's about the crisscrossing of different members to build up capacity and strength, or to be able to span different distances. Because obviously if you want a structure to go from one place to another, it has to be able to support its own weight and the weight above it that's on it for the length of that distance. So sometimes that means that members can get a bit taller. One of the terrific opportunities that you can, and this is actually just a bit of a repetition of what we've already covered, so the C-shape, structural tubing, they've called this it looks like they've called it an S and a W, I'm not quite sure what that's all about, but this is an I. See here, these are the flanges that I was talking about. These ones are parallel to one another. See, these ones are chamfered slightly, so that's not parallel. So just be aware that channel, which is non-parallel here drawn, channel can be either parallel or not parallel, and I-beams can be parallel or not parallel as well. They just do different performance. I mentioned these are the flanges. This is the web member in the middle as well. And in the light-up referee, there are dimensions for all the different pieces. You can specify the width and the height and the thickness of the steel. So the other thing that you can do, which is quite nifty, is you can cut those webs in a, I don't know what they call this, a castellation, I think, is that right? Yeah, cut it in a castellation, and then you can simply pull them apart, offset it a little, and weld it back together again. The height is increased, the amount of steel is the same, but the height is increased, and it does leave space for conduits and pipe work and service ducting to go through, and it performs differently when you're able to do that, so it's quite nifty. Or you can also create, if I can just scroll down a little bit, you can also create, a little bit further, you can also create open web joists with pipe or tube or steel structure and top and horizontal, bottom horizontal sections to create a span that will go a lot further as well. They look almost like a truss. Have you? Yeah. They can span quite good distances. They're very lightweight. And you can see the triangulation that's nice and strong. That's where the strength in compression comes in. It works really well. You can see it in a full system there. So this one's connected to a solid wall on this side and then an open structure on the other side. Goes on a little bit further with regards to the metal decking. So there's the metal frame with the concrete on the top with added fabric reinforcing and composite decking as well. I won't delay on it too much. Now what I want to do is skip to the section that shows you about AT3 construction. So this textbook has labelled them rigid steel frames. So section 6.07, around page 200. So it says rigid frames consist of two columns and a beam or girder that are rigidly connected at their joints. Applied loads produce axial bending and shear forces in all members of the frame, since the rigid joints restrain the ends of the members from rotating freely. In addition, vertical loads cause a rigid frame to develop horizontal thrusts at its base. A rigid frame is statistically indeterminate and rigid only in its plane. All sounds a little bit fancy. I'll just see if I can get this on the screen on its own. What you're seeing are vertical columns connected together with rafters, basically. So this is one single piece that goes up and over and down. And we call it a portal frame. It can create very, very large open column-free space. It's that simple. It's a very, very simplistic structure. It's probably it's very strong, but with very minimal construction. Very minimalistic construction, if you like. The members are normally universal members. So the I shape, universal column, UC, and UB up here, universal beam. Then on the top, you'll see they're all connected together, so they're set out at a grid. So the individual pieces set out in a grid, and we'll have an indication of where that grid might be on our sketches already. You'll see the eye in plan view, but they can't stay up on their own. So they might be connected to the ground with the pad footing and the pile pier footing and the reinforcing inside, but if they were to remain just this one piece, it would simply just topple over like dominoes. So they're kept apart and upright and fixed in place with framing members that do support, but also allow you to apply a skin, a sheet fixing to each one. Often the grid spacing is determined by what the span is of the girt on the side and the purlin on the roof can achieve, or by perhaps the roller door that you want to include between them to save you from having to do a skin, or by whatever forklift you need to get through or trucks you need to get in. There's lots of different reasons why you might choose the span and spacing of the frame. So on the side, you'll have usually this stuff, C-section. There's a Z that's the same type of material, but it goes, this side goes up and out. So this one is down and this one is up. Do we have one? Oh, we do. forgot that we have one. So this is a C, and that's a Z. Look at that. Pass the Z around. And they can act in horizontal plane. Oh, there's two. They can act in a horizontal plane, and when they go around the outside of the building, they're called girts. And they also can go on the roof.
Yeah, it's just when the edges they are quite sharp.
And they become purlins. So it's the same steel, maybe different sizes depending on the span and the loads, but in the horizontal location on the sides, they're called girts, and on the roof, they're called purlins. And they're usually equally spaced apart, so say 900 millimetres apart as a guess.
So your centre to centre of your purlins and girts might be determined by how often your cladding needs to be fixed to that. Your cladding would probably be, say for instance on a warehouse building, you probably have considered the metal sheet cladding, and the deemed to comply will tell you how often it needs to be fixed, how many centre to centre, especially in a cyclonic area like we are. And then that will determine how often you see these or what centre to centres they're at on your wall and your roof.
Yeah, can you use that?
One of the biggest risks with this kind of construction is the wind loading. On any wall, it's under significant pressure from wind loading, but particularly in this direction, front to back, because obviously this is the pivot point where everything could just go unstuck. So you can see here they've specified some cross spacing in this bay. Typically you will see it in every bay that doesn't have a door. So as often as you can, and then you can also see it in the roof plane as well. So either a big X or two smaller ones. The other thing, and you can't see it on this diagram, but I think you'll see it in the details below, is it'll also be bracing from the underside of the purlin down to the top of the web member of the rafter. So if this is this member here in section, and this is my purlin going across the top, took me a second there, whew. You'll get a piece coming down this way that's either welded or bolted, and it's called fly bracing, and it'll either go up to the flange or just sit underneath. So it's an extra bracing, probably should have brought it down a bit, it's actually down here. So all the different sides are braced, so the wind can't push it because it's just a big balloon being hit on by strong winds. I'll just scroll down and see if there's some detailed drawings that are better than mine. Yes, that was quick, wasn't it? The other part that you would have heard when I read that out was about how it can be fixed. Now, that's not always the case, but we've got a vertical piece here and then an angled piece here, and they're connected in the corner. So that's a fixing. Same with the ridge and the other apex. So there needs to be a connection between the two pieces of steel. There can be no movement allowed, or there can be some movement allowed, and it just depends on the engineer's choice about how he's going to manage that with regards to the purlins and the girts and the sheeting and everything like that. So typically it's fixed, but there can be a little bit of movement. If it's fixed, you might often get an extra piece that just comes across this way, called a gusset, that just really seals that up and makes sure that there's no flexibility there. And that's all we get about that.
So before lunch, question was asked, like, how much of this you need to be able to design as a building designer as opposed to being the actual structural engineer. Like, a couple of things Lisa was talking about there may be impeding on your architectural design or your building design, where the bracing is going if you want to locate roller doors. So that's the conversation you're having with the structural engineer. I need to have, for functionality of the building, 3 roller doors, and we've got 4 bays. And then that's a two-way conversation with the structural engineer. Is one bay with bracing in it going to be sufficient to stabilise the building structurally. And the other things you look at are those flange pieces. If you're going to try, if for instance this isn't just an open warehouse for industrial use, you could be building a portal frame. Many of our buildings here at CDU are portal frame. You may be wanting to line the whole building internally. How are you going to line all of those columns, all of your I-beams or I-columns are going to be vertical? Are you going to box them out? How do you do that? How are you going to frame them out? If there's flange pieces, are you going to see them in the room? For instance, if there was a portal frame immediately above us here and there was a flange piece here, is that going to impede in your internal space? Are you going to see it? Are you going to box it out? Is it going to be in the ceiling cavity? So all of those things, it's really good for you guys to be aware of the structural members so you know the impact they might have on your architectural design.
There's a couple of good recent examples on campus. We might go for a bit of a walk and go and have a bit of a look after the break. Pink 9, the main trades building, is a portal frame shed that's where classrooms are and office spaces and open structures, roller doors for downstairs, all sorts of nifty little contraptions. So.
Alex was just telling me he got a set of drawings for Purple 9.
Yeah, that's the one. Yeah, I've got them too.
9,
Yeah, Mo did that.
Yeah.
All right. I'm just going to go back now to where we were. I confess I'm going to skip a lot of the floor framing and timber framing because we'll either cover it later or it can just be knowledge that you'll pick up along your career.
Of course, you can flick through the book yourself and get a general knowledge of all of these things. But, you know, as we said, like if you were studying to be a structural engineer, yes, you're going to have to know every single system and how it all works together. For what you need to know, it's good to know where you can find the information and to know that you have to analyse each project and identify the structure. Always you need to know what structure you're going with in each building and understand it.
Just as a little extra piece of information, that neighbour, that poor neighbour that I keep referring to, there's such a terrific example of how things can go wrong. That neighbour wanted to extend and they weren't able to resolve the construction connection to the existing house. So, and they probably will still go ahead with that, but at the back of the block, which has got hard to have access to, they wanted to build a shed out the back. So it was pretty likely going to be lightweight construction because of the unstable soil, but they still wanted to have a concrete slab on the ground, and we discussed just informally about how that might be achieved, and I suggested that perhaps in plan view in the shed layout, rather than having a construction system that has the structural frames connected to it, so a slab on grade or on the ground that would have the structure connected to it, that then needed to have footings beneath it, which would then be a bit uneven in movement, that perhaps what he could do would be to have footings, so I don't know whether he ended up using eyes or squares, but have footings that are independent of the slab in the end. So these triangles represent the pad that we've been seeing in detail for each of the pile footings that he would have needed, and then the slab itself can be independent of that, and then you can have silicon, significant amounts of it, that will accept some small amounts of movement differentiation between the big slab and the independent, deeper footings that were allowing the structure to sit above. So the structure and the floor slab are actually independent of one another and could move independently, because that's likely, because the dead load is completely different. The live loads are completely different for this space as they would be for the structure itself that sits independent. I don't know offhand whether he actually went with that or not, but he bought a kit shed and built it himself. So probably not quite right. All right.